Okay, we're going to get started with Scott Burleigh from JPL talking about what's new with ION, and it turns out there's quite a bit because he's been very busy.
Great. Thanks. This is the speaking slot immediately after lunch, during which everyone traditionally falls asleep. Please feel free. I'll say things that you may pay attention to or may not, and that'll be fine either way. Next slide, please. So what I'll be talking about is the latest work that's been done in the Interplanetary Overlay Network implementation of delay-tolerant networking, ION. And just by way of background, I'll do a couple of slides sort of showing where ION comes from. This is, of course, old news to everybody. The terrestrial internet is characterized by continuous end-to-end connectivity and very brief round-trip times. In the solar system internet, we're expecting to need to be able to handle intermittent point-to-point connectivity and very long round-trip times. Next slide. So this may or may not be obvious to everybody here, but there are constraints on operating delay-tolerant networking in space that are somewhat different from the constraints on DTN and terrestrial networking. In terrestrial DTN, we have typically Ethernet or Wi-Fi links, which are fast and they're cheap and they're typically symmetrical bandwidth. We have CPU and memory that are fast, cheap, commodity generic chips, very powerful. We have, there are some operational advantages. Rebooting is easy. You push a button on your machine. Dynamic management of memory is routine. In the event that you run for so long that some latent memory leak shows up, you just reboot the machine. It's not a big deal. And the operating systems typically are commercial operating systems with memory protection modules, so that you can have multiple things with their own memory. Nothing steps on anything else. Tasks all run in user space, and there's a lot of operational safety from that. In deep space, in spaceflight operations, in many cases these things are just not true. The conditions are somewhat different. The links, certainly for deep space and to an extent even for Earth orbiting missions, are directed radio or directed optical. They tend to be highly attenuated because they're very far away often. They're relatively slow compared to what you can get on planetary, on the surface of Earth, in the internet. They're very expensive. They're often asymmetrical. That is, the rate at which you receive something from a spacecraft may be very much higher than the rate at which you can transmit to a spacecraft. And so you have to use reception and transmission contacts very efficiently because of these kinds of constraints. Similarly, in spaceflight, because of the radiation environment being very hostile, you typically need to use limited production radiation-hardened electronics. These are relatively slow and very expensive because there's a small market for them, so they don't get built in large quantities, and so the cost of developing these radiation-hardened electronics is not going to be amortized over billions of units, but only over hundreds or maybe even fewer. And so the processing resources are scant and need to be used efficiently also. Operationally, you're not going to be able to push a button. On the space station, you actually can, because you have people there, although it's a difficult thing pushing a button on something that's mounted on the outside of the space station. But for anything in deep space, for the foreseeable future, you're not going to have people available to press a button and just reset the machine.
That's what robots are for.
Yeah, right, yeah. But in general, hands-on repair, you pretty much can't do it. So you really build these things for for very high durability and robustness. And part of that is that management of dynamic memory is typically frowned on by flight managers, because if you do have a leak, you wipe out, you use up all the memory on the spacecraft, and then you have to reboot, and it's a bad thing whenever you have to go into safe mode on a spacecraft. So typically, memory management is there's a fixed amount of memory that you're allowed to have for every operation on the spacecraft and the flight software, and that's allocated at startup time. And then not all, but many spacecraft are operated using flight computers that have real-time operating systems, at least as the attitude control and very often the command and data handling processors as well. So there's these real-time operating systems. Typically, there isn't any memory protection. I'm thinking of things like VxWorks, where everything sort of runs in the same memory space, and so it's you don't have the same advantages of memory protection that you have in, say, Windows, for example. Next slide. So the design of ION was intended to address all of those constraints. It has its own built-in private memory management system, so that you can allocate one fixed chunk of memory to ION at the beginning of the mission, and ION manages it privately from then on, and there's never any subsequent allocation of system memory. There's a built-in object database for data management, and that's a high-speed and highly reliable object database system with a transaction mechanism that's built in to enable backing out partial updates to the database to avoid data integrity problems. That same transaction mechanism also is used to ensure mutual exclusion, so that you prevent race conditions and lockouts. The bundle headers, the DTN implementation for DTN for ION was the first one to use compressed bundle header encoding, because we wanted to be able to shrink the bundle headers down to a small size for transmission, for economy in using the bandwidth. Zero copy objects. These are it's a mechanism for minimizing not only the amount of space that's occupied by data, but also the amount of time you spend copying it from one buffer to another. If you've got a multi-megabyte bundle in ION, it'll live in one place and it'll never move from that place. And all that happens is, as you process it through the various daemons in the system, all that happens is that pointers to it are moved, and the pointers are sort of elaborate pointers that enable you to virtually prepend and append headers and trailers to that data without ever touching it. The whole system is written in C for processing economy and to keep the footprint small. At the time I put the slide together, it was about 60,000 physical lines of code. It's probably a bit more than that, because we've added some functions since then. Still, I'm sure under 100,000 lines of physical code, and logically quite a lot less than that if you take out white space and comments and so forth. And it's highly portable. The ION system ports pretty easily among POSIX-based operating systems. It's also ported to Windows, and it's ported to Windows, I would say native Windows. That is, when you compile ION for a Windows environment, it creates native Windows EXEs. You don't need to run in the SIGWIN environment, for example. You just run in Windows. You need MinGW library to do the development, but the operating environment is there's a MinGW library that fills in some gaps, and otherwise you're using vanilla Windows. Next slide. So this is the design of ION in a nutshell. Really, this is pretty much all that goes on. The object database I referred to before is this thing inside the dotted lines there. Those round things are non-volatile linked lists, queues of bundles. And essentially all that happens in ION implementation, in the ION implementation of DTN is an application issues some data. It gets wrapped in a bundle and placed in this queue of bundles to be forwarded. A separate routing daemon running at the same time pulls things out of that queue and determines where they're going to go and appends them to a different queue for transmission. And there could be any number of these different queues for different out ducts. We call them different convergence layer adapters for transmission. Then the out duct itself is this little block down below that has a sender library that pulls data out of that linked list and uses convergence layer protocol to transmit. Here I'm showing loopback, but that's a dotted line between transmit and receive to show that it could be loopback or it could be transmitting to the receive module at another node altogether. And the receiver, another task running concurrently, an induct, receives the data, then invokes a dispatch function that either places the received bundle on the queue of bundles to be further forwarded, or else places it in the queue of bundles for delivery, and the application running asynchronously with everything else, calls a function that causes the data to be delivered out of that queue and passed to the application. That's really the whole of ION. Everything else is making all that stuff work. Next slide. The design principles of ION kind of grow out of the constraints that I talked about earlier. And there are three that are most notable, I think. One is shared memory. You often don't have protected memory. Well, that can be a danger, but it can also be a strength because shared memory is a very, very fast way of moving data around. So as a sort of killing two birds with one stone, we in ION we try to leverage the use of shared memory to improve performance, and we have to deal with it anyway. So we have to design carefully in order to avoid problems that can come out of careless use of shared memory. So a typical structure in data movement in ION is that the data doesn't move. It goes into a linked list, which is residing in the object database. The sender just puts it onto the linked list and gives a semaphore. The receiver takes the semaphore and reads it from the linked list. Zero copy procedures, these are the zero copy objects I was referring to earlier. Again, leveraging shared memory to minimize the processing overhead. All the data is encapsulated in multiple layers of protocol overhead, and that's all done just by accounting, not by actually copying things into buffers. And that also enables the same data object to be shared by multiple tasks, so you have reference counting instead of multiple consumptions of the same data. And then portability. I mentioned before that ION is designed to be extremely portable, and that's because the shared memory, non-protected memory kind of and real-time operating system environment is, I know from personal experience, a difficult environment to do software development in. It's much better, much easier to do your development in, say, Linux, and then recompile it for VxWorks than the other way around. So portability is important, not only in terms of exposing the software to the widest possible market, but also in terms of making the development easier. It's much easier to do the development if you can port it after you've made the changes to the Linux code, for example. Next slide. The first major demonstration of the ION code was in the Deep Impact Network experiment we did in 2008, where the Deep Impact mission, Comet mission, had been repurposed to explore another comet. That is, the Deep Impact was 2 spacecraft. There was an impactor that crashed into a comet. There was a flyby that took pictures of that, and then the flyby survived, went on to visit another comet, and while it was en route to another comet, we borrowed it for about 2 months and loaded the ION software onto the spacecraft and operated it as a router in deep space. At the time, it was, I think it varied between 81 and 49 light seconds distance from Earth, around a maximum, I think, around 15 million miles. And we uploaded data from one node inside Building 238 at JPL to another node inside Building 238 at JPL, but through the spacecraft. You know, this spacecraft was a router, so the round trip time was on the order of 100 to 160 seconds. And that worked very well. It was a quite early version of the ION software, but it still was quite successful in moving data without data loss through the course of multiple deep space network contacts, resulting in really effective round trip times of up to 2 days. So it demonstrated some quite solid delay tolerance and robustness, because on a couple of occasions we had deep space network antennas that failed in the course of doing transmission, and the ION software recovered from that. Next slide. So here's a brief history of the progress of the ION development so far. It really sort of goes back to about 1996, when some of the infrastructure that ION is based on was developed in the flight system testbed at JPL, the dynamic memory management, the object database, and the portability layer. We began doing IPN and ultimately DTN research in late 1997, early 1998. The first prototype implementation of DTN was DTN1, and that was done in middle of 2002, I think. DTN2 was started about a year after that, and the beginning of the ION implementation as an implementation of DTN itself really started right after that in 2004. So the bundle protocol implementation and the zero copy objects implementation happened in 2004. 2006 and a half, the BP bundle protocol spec was published. The LTP implementation and contact graph routing were added to ION about, toward the end of that year. Deep Impact was 2008, and in 2009 we began running those CGBAs on ISS. Those were running ION. The implementations of the CCSDS bundle file delivery protocol and the bundle security protocol came along at the end of 2009. The Windows port was 2011, I think. Bundle streaming service, which is aimed at enabling continuous streaming of video over DTN, came on a little bit after that. A multicast, a delay tolerant payload conditioning, and the port of DTN Perf, the DTN performance evaluation system developed at the University of Bologna, came in toward the end of last year. And at the really close to the very end of 2014, we worked on improving the port to the common flight software for AES missions. And then at the beginning of 2015, an implementation of the streamlined bundle security protocol and bundle-in-bundle encapsulation. That sort of brings us up to where we are now. So next slide. Version 3.3.0 of ION was released at the early part of March. The focus there was really security, and this was the SBSP implementation and bundle-in-bundle encapsulation for cross-domain solution to security. And it also included dynamic computation of the reporting limits in LTP to enable large blocks to be transmitted in fewer iterations and with less reforwarding. And there was also improved support for ISS operations, working with Tyler to get flow control for the simple TCP convergence layer working well for the ISS operational environment. Next slide. The most recent work, and this is less than a month ago, ION 3.3.1, a point release was issued. That included some additional features and bug fixes, mainly aimed at supporting the ISS deployment. There were some things that needed to be done on the Windows port in particular, in semaphore management that we hadn't noticed before until we started doing some heavy testing in Windows. And there was a sort of an obscure feature about dynamically rebinding TCP connections that turns out to be very useful for the way ISS is going to be operating the TCP convergence layer. There also were a couple of other bug fixes that came out of the CCSDS bundle protocol interoperability testing with JAXA, testing between ION and DTN2. And as part of that release, we also slipped in a couple of updates to the ION tutorial, which was many years out of date by this point. Next slide. So next coming up, and this is, the target here is early July. That originally was going to be end of May, but it was really important to do the ISS work, and so some of this other work slipped a bit. So we're at least a month behind on getting the 3.4 features out. But we're getting to work on it now. The focus there is on terrestrial DTN, on being able to use the ION implementation not only for spaceflight missions, but also in the sort of opportunistic and probabilistic terrestrial DTN forwarding environment. So that includes an implementation of the contact discovery protocol that's being done by the topcoder community, and there's actually been an almost complete implementation of that done now that looks like pretty good code, the little I've seen of it so far. We're going to need some sort of a protocol for exchanging contact plans between nodes that opportunistically discover each other. And the rationale there is there have been a very large number of routing schemes developed for opportunistic forwarding in terrestrial DTN. And my hypothesis here is that that the contact graph routing that we've been using for routing in interplanetary networking is actually a good way of doing opportunistic terrestrial networking for routing as well, because it's based on the best available knowledge of the topology, like all internet routing protocols, rather than sort of just being behavioral. That may or may not be true, and that's what we're going to discover as we press ahead with this. But the idea there is that the contact plan that you use for computing routes through the space network is based currently on contacts that are scheduled and anticipated, planned, and will happen with some very small probability that something will be missed. If we add to that structure contacts that we think will happen, that have some probability of occurring, that maybe we learn from contact with other nodes and exchanging what we know of each other's past history, then we can build a contact plan that doesn't have as much certainty in it, but has a certain degree of probability that is maybe reinforced by continued contact. And we can use that as the basis not for saying, okay, it's going to go this way, so I'll send the copy this way and I'm all done, but instead saying, it might go this way, so let's send a copy that way and keep track of the fact that we did it and we have some degree of confidence that it'll work. And let's do that again, and then again, until finally, at some point, we've sent enough copies that we have enough confidence that we think, oh, well, now we've probably done it enough. And at that point, discard the copy of the bundle that has been transmitted because you don't need to transmit it anymore. So that involves inference of probabilistic contacts, which also is a kind of a research problem. We'll do something primitive, I think, for the 3.4.0 release and try to refine that over time. And the last point there is that the motivation for a lot of this stuff is that for flight operations, the end-to-end network that we use to operate spacecraft includes people who might be in charge of operating instruments or elements of a spacecraft that are not necessarily at their desks at the time something happens. So you need to be able to reach out into the terrestrial network with opportunistic forwarding to reach those people. The ground operations are an important part of the end-to-end spaceflight operations network. Another possibility for 3.4.0 rather is the delay-tolerant key administration system that we've been working on for about a year or so. That's in the process of being approved for open source release within JPL. It may or may not happen in time for the 3.4.0 release. If it does, then I think that'd be a good thing to get out as well. Next slide. Looking further ahead, 3.5.0, and this is the target. The original target for this was end of the U.S. government fiscal year 15. It may slip a little beyond that. And the focus that I have in mind for this is scalability. It's great to be able to do terrestrial networking, but it's not going to solve a lot unless we are ultimately able to scale it up to very large, the very large number of users that we expect to see in a terrestrial network. And so my thinking here is that we're going to need some sort of registration that will actually not be delay tolerant necessarily, but will be sufficiently delay tolerant for the purposes for the limited purposes of registration that I think we need to have in order to have scalable routing, which I believe is going to depend on being able to carve out regions within which contact graph routing can work. Contact graph routing itself, it seems unlikely we're ever going to be able to get CGR to scale up to more than somewhere between 50 and 100 nodes and operate quickly. And so I think in order to scale up to a large network, we're going to need to carve up that large network into something very much like the Internet's autonomous regions that conduct CGR within them and then have some sort of a BGP-like protocol that manages forwarding of data from one region to another through gateways that are well known. I think that auto configuration of nodes is going to be pretty much required for this, because we're not going to be able to do the sort of node management that we can do for spaceflight missions if we're going to have 1 million or 100 million individuals participating in the network. And I think that ultimately multicast is going to be key to making this work. I think that when nodes join this network, they're not going to know what every other node in the network is prepared to send to them, and who they are, and what to send to them by any way other than multicast. And I think that's a doable thing. We have a multicast implementation in ION now, and I think that that building that capability out is going to be really key to making scalable terrestrial ION work. Next slide. Looking out after 3.5.0, one thing that's certainly going to need to happen is, as the Internet Engineering Task Force DTN Working Group comes up with new definitions of the protocols, revised specifications for bundle protocol and bundle security protocol almost certainly, and probably a few others as well. We'll need to reflect those changes in ION. I think that's, so far I'm not concerned about that. I think it's going to be relatively straightforward, and if anything, it'll make, if things follow the direction that I'm hoping they'll take, it'll make ION simpler and somewhat smaller and easier to manage. Again, coming back to multicast, there's the BP multicast that is built into ION has a reliance on an underlying spanning tree, which is currently managed by administration, by management, and that needs to be automated. We've had a design for a spanning tree maintenance protocol sitting around for several years, and at some point somebody's going to have to bite the bullet and actually implement that. And I mentioned this earlier, having contact plans, including probabilistic contact plans that cover the terrestrial delay-tolerant networking environment, gives us the ability to compute to some degree, to some probability, the expected delivery time for a bundle, and that in turn gives us the ability to support congestion control even in delay-tolerant networking. In terrestrial delay-tolerant networking. I think that's again conjecture, but I think that's a function that we're going to be able to get given contact plans that cover the whole, that cover the terrestrial networking environment. I think we can use those for accurate, relatively accurate congestion forecasting and time to live estimation to control congestion. Next slide. Then further off, and even less fully thought out at this point, the registration infrastructure that I think we're going to need for scalable terrestrial DTN anyway, I think ultimately can be used to implement configuration of new nodes in a more powerful, more useful way. To be determined. We haven't even thought very much hard about this yet. And then the last thing, which I think I also mentioned earlier, and we just give a little bit of background on this. Back when the DARPA funding for DTN was the main source of development, and this is in 2005, 2006, 2007. The program manager for that DARPA DTN project was Preston Marshall, and the thing that he really wanted to see come out of that work was what he referred to as a self-forming Akamai, that is sort of automatic pre-placement of data that combat units would need that they didn't know they needed yet, or that you wouldn't be able to get to them because they're out of contact. But if you could pre-place it, then when they did need it, they could ask for it and it would already be there, and they wouldn't have to come all the way back to Columbia to get the data. If you take a step back and look a little sideways at that, and that looks similar, very similar to what's being called information-centric networking as developed over the last 4, 5, 6 years. I think, and this is a personal opinion that is yet to be validated, that ICN, as it's been developed so far, is a great concept, but I think it's using the wrong. I think it's using the wrong technology. It's based on the naming of objects. I think what would be more powerful is to base information-centric networking on the content of objects, and to do that with multicast and with search engines embedded inside the multicast nodes. So I think that a DTN-based ICN approach is ultimately going to be a more powerful way to accomplish information-centric networking, and I look forward to having a chance to work on that in a couple of years. And I think that's all my slides. I've got some backup slides, but I'll stop there and ask if there are any questions.
So a couple things that I found very interesting with this presentation. The first was the mention of the opportunistic networking. If you remember earlier when I was answering a question, I mentioned that.
Mm-hmm.
I didn't really know that you were working on that as a contact graph integration.
And there's actually, I think maybe there's sort of, in a sense, there's two dimensions to that. There's opportunistic networking where you know who you're going to talk to and you don't know who yet, or you don't know when yet. And then there's opportunistic networking where you don't even know who you're going to talk to yet. The former, I think we've made pretty good strides toward for ISS, where when the contact is there with somebody that you expect to talk to, you pick it up and you begin to use it. The new thing that doesn't exist yet is opportunistic networking with somebody you don't know. They just randomly bumped into you and you say, oh, well, okay, let's talk.
Great. I actually have another question if nobody else has an answer. The other thing I've been working a lot lately in is LDAP.
Oh, yeah.
Very tangentially,
Yeah.
in preparation for getting
Yeah.
ION put on stage.
And I think the registration stuff that I've been talking about, the first thing that came to my mind was I was looking at it was this, we need to do this with LDAP.
I'd be curious to see about a DTN-ized LDAP synchronization protocol. That'd be kind of...
What a great idea. Yeah. Let's think about that.
And there is a question from the webcast.
Sure.
And again, this is from Scott Johnson. And he's asking, how does the size of the block of memory that's assigned to ION vary? Is it, for example, a variable passed to the kernel at boot time, or is there some other mechanism?
Good question. It's a configuration parameter that in the ION world you supply at the time you instantiate the node. It is fixed for the life of the node, so you want to take a pretty good guess at it, or else you want to be able to save state off to some other medium, and then just blow the node away and re-instantiate it with a larger fixed size, and then reload it. historically, that has not been a big problem. The nodes that we use in testing and in operations so far, we typically allocate sort of as much storage as is comfortable, and just and live within whatever that amount is.
So it's kind of driven by the hardware configuration that's available.
Yeah, there are, and let me moderate that in one way, which is to say that for an operational deployment, if you instantiate your nodes and run some testing, there are tools provided in ION for inspecting how much non-volatile database heap space you're using, what your high watermark is, and what your high watermark in working memory is. And if you do a full round of testing for a few months and record those numbers, well, chances are when you instantiate the real operational nodes, if you take those numbers and add 50%, you're probably using your storage resources fairly efficiently.
And this is for me. So what is driving the requirement for multicast in a DTN environment?
Yeah, well, I think it's a couple of things. One is, looking down the road, I don't see any way other than multicast to really inform nodes efficiently about what one another wants to see, right? And it's there's a profound difference here between DTN and what you typically do in the internet. In the internet, you can do query-based, client-server operations because your round-trip times are small, and that's a standard mode of operation for applications is client-server. In a DTN, you can't necessarily rely on being able to do client-server. You can't necessarily rely on being able to do an efficient conversation. What you need to do instead is convey information in advance to the nodes before they need to act on it. And multicast is a perfect vehicle for that. You convey to everybody, here's what I want. Whenever you get around to having it, send it to me. I'm not going to ask for it. I've already asked for it. This is it. So there's a fundamental, very close fit, I think, between multicast and the natural way that the DTN operates. Narrowing down a little bit more closely, the delay-tolerant key administration system that we've been working on for a year or so relies very much on multicast because it's based on a collaborative authorization of distribution of public information, and multicast is very key to that. And I think that there will be other applications for really trustworthy, robust data distribution that model is perfect for. Not just key distribution, but other kinds of critical information for enterprises of any kind. And all of that is going to be ultimately based on getting multicast working right. So I think multicast is really central to the future of DTN.
You need the, okay. I apologize for having to duck out for a phone call. What about node discovery? Did you already talk about that? Because multicast sort of makes me think of node discovery or node announcement.
Yeah, absolutely. This is something that we're going to be we're starting on, in fact, now for the 3.4.0 release of ION, which we're targeting July. It may slip a little bit, but at the moment we're targeting July. Part of that is going to be the focus of the 3.4.0 release is going to be adapting ION to terrestrial networking. And a big part of that is, I think of it as contact discovery rather than neighbor discovery. Once you've discovered the contact, you can infer the neighbor. The implementation of the IPND RFC, I think, is already being undertaken by the Topcoder group, and they've got an implementation. They've got code. It hasn't been fully integrated yet. We need to integrate it and test it, but I think they've made pretty good progress on that, and I think that's really a precondition to any of this stuff. Yeah.
I had an interesting, painful experience this weekend with a protocol called Bonjour, which has been rewritten for the latest version of the Mac operating system, and didn't seem to work as well as the previous version. But I hadn't appreciated is how many places that particular kind of discovery protocol is now being used. I mean, it's lots and lots of devices participate in that
Sure.
to make themselves visible.
That's going to be like, you have to have that for Internet of Things, right? I mean, how else can you make it work?
Exactly. How else would you figure it
Yeah.
out? And then you have the problem of making sure that you're not configuring in your neighbor's stuff, and the 15-year-old isn't configuring your stuff and all that other stuff. So the reason I bring it up, though, is that this could turn into an extremely important aspect of the DTN protocol, because the more I think about Internet of Things and battery-based things and devices that are trying to be thoughtful about their duty cycle and everything else, that the need to have these discovery mechanisms is going to escalate. So I'm glad that you are thinking about that.
Let me add something to that. This is sort of fortuitously at the last IETF. I talked with a couple of guys from, I can't remember, I think it was Airbus, who have been working on, in another IETF working group track altogether, on essentially a contact discovery mechanism that is at a lower layer. It's an RF contact discovery system rather than an IP contact discovery mechanism, which I think is has a lot of potential. I think there's a lot of potential value there. They're very interested in integrating with the work we're doing.
I think you're talking about neighbor discovery.
Pardon me?
You're talking about neighbor discovery?
Yeah.
Okay.
Yeah.
And that would be the guys from Airbus, because they're in the man-A
Yes.
community.
Right.
Yeah.
Yeah.
Well,
And I should, John Dowdell, I think, was one of them.
Dowdell and Rick Taylor.
Yes, that's right. Yeah.
So, it's fair to observe that radio has this potential to be heard in more than one place at the same time, and that makes it useful for this sort of broadcast discovery mechanism. Okay, anything else before we finish up with, okay, so I guess we should thank Scott.